alternating series. Here, if we have a series where the values are said to oscillate between two fixed points like plus or minus 1 or what have you, and you can determine that by the negative 1 to the n factor or negative 1 to the n plus 1. Anytime you have a series that has negative 1 to the n or negative 1 to the n plus 1, it is automatically an alternating series. Well, we can use the alternating series test to determine whether or not the series will converge or diverge. Here, let's make sure that a sub n is positive. The alternating series is one or the other, the summation of negative 1 to the n times a sub n, or the summation of negative 1 to the n plus 1 times a sub n. The series converges if both of these two conditions are true. That is, that the limit of the sequence values, you get 0, and also that the sequence values are decreasing. They're getting smaller as you count n. So with that in mind, let's consider this. And you're going to notice that something startling happens. This is an alternating series with the limit as n goes to infinity. Here we take the limit of the sequence values, n plus 1. We get 0. Secondly, the sequence terms are decreasing. So if that be the case, then by the alternating series test, you have this guy right here. Therefore, by the alternating series test, the series converges. Now what's startling about this? That if you remove the negative 1 to the n plus 1, the series would diverge. You see that? So let's consider that. This is p-series divergent, right? Harmonic divergent. So what's the difference? What's making this alternating series converge in comparison to if you remove the negative 1 to the n plus 1 and we get divergent? Let's see. There must be something with that negative 1 to the n. So if you remove that negative 1 to the n, that is, take the absolute value of the sequence of terms for the series, and if that result converges, then the series itself without the absolute value also converges. Now, there's a play with that, and I want you to see it here with this definition. This is the definition of absolute and conditional convergence. The series, the summation of a sub n, is absolutely convergent when the series of the absolute values of the sequence terms converges. The series converges, what we say, conditionally, when the series without the absolute value converges, but when you take the absolute value of the sequence values, those terms diverge. So we have conditional or absolute. It's absolute if in both cases, with or without the absolute value sign, I get convergence, absolute convergence. Or with and without the absolute value signs, one converges, the other diverges, is conditional. The condition is with the absolute value, the convergence changes. Let's see. So look at this problem. Here, just determine whether or not it converges or diverges. Well, without the negative 1 to the n, it's geometric series, convergent. So here it's going to converge even for the alternating series. So 1, it is an alternating series. 2, the limit as n goes to infinity of 1 over 3 to the n goes to 0. And 3, 1 over 3 to the n is decreasing. So therefore, by the alternating series test, this series converges. For the next one, is it an alternating series? Yes, it is. What about the limit as n goes to infinity of 5n minus 1 over 4n plus 1? This limit is equal to 5 over 4. It's not equal to 0. It's not equal to 0, right? It's alternating series. Matter of fact, these terms are increasing because 5 is greater than 4. So this particular series diverges. It diverges based on the alternating series test, and because it fails both of the criteria, that the limit has to equal to 0 and that the sequence values must decrease. And it also diverges by the nth terms test for divergence. The next one is an alternating series, yes. What about the limit of the sequence terms of 1 over the square root of n? It is 0. 1 over the square root of n is decreasing. So we conclude, therefore, by the alternating series test, the series is convergent. What about this one? Is an alternating series? Yes. What about the limit? We have to investigate. The limit is n goes infinity of n plus 1 over the natural log of n plus 1. But here we get infinity over infinity, so we have an indeterminate form, so we apply L'Hopital's rule. So this implies that we have the limit as n goes to infinity. The derivative of the numerator is 1. The derivative of our denominator is 1 over n plus 1. This is the limit as n goes to infinity of n plus 1. And this is infinity. And so, if that is the case, here we have divergence. What about this one? It is an alternating series. What about the limit? The numerator is less than our denominator. This is 0, and the square root of n over n plus 2 is indeed decreasing. So we conclude here that the series is convergent by the alternating series test. Now these problems here you want to determine not just is it convergent, but is it conditionally or absolutely convergent, or does it diverge? So this problem here is an alternating series. Is alternating series convergent? So by itself it converges. Now take the absolute value which is the summation as n goes from 1 to infinity of 1 over 2 to the n. N. How come my n's don't look like n's? This guy is geometric series convergent. So it converges both ways. By itself, it's alternating series convergent, and then remove the negative ones to the end, and it also converges. That means that it converges absolutely. I'm looking at my watch, my phone over here. My friend's supposed to be coming to take me to lunch, so I don't want to miss my ride. Free ride. So here, it converges absolutely. What about this one? Is alternating series convergent? Now, if you look at the absolute value of these terms, my writing is bad, but I think it's this stupid computer, not the computer, but this program. It's making me sick. I'll tell you what is making me hungry. I know that. I sense chicken in your future. So this is the summation of 1 over the square root of n, which is p-series divergent. Because p is 1/2, right? P has to be greater than 1 for convergence. P-series so it converges for one case, but it diverges for another, so it's conditionally convergent. One more. Oh, goody. We get to go to eat now. We get to get something to eat. Now, let's see. Oh, this is good. It is an alternating series. You have the -1 to the n plus 1. The question is it convergent? It is, because the limit as n goes to infinity of n squared over n plus 1, this guy, I was supposed to go to 0. This guy doesn't go to 0. I'm sorry. This limit is equal to 1, right? You get the n squared up top, then downstairs you get n squared plus 2n plus 1. So they have the same powers. So the limit is the ratio, leading coefficients, 1 divided by 1. So this guy is alternating series divergent. Right? So it's alternating series divergent. That it is, my friends. That it is. Which seems to be strange, but if we look at those terms, it's just n squared. The bottom becomes n squared plus 2n plus 1. Indeed. The limit is fine. The limit is 1. It's just not 0. That's the only thing. And for the alternating series test, the limit has to be 0. The values must be decreasing, which they are. But since the limit is not equal to 0, excuse me, we need to use something else. Okay. Now for the alternating series, it does diverge. The sequence terms they are decreasing. By the alternating series tests here, the series diverges. Let's check to see what happens when we take the absolute value. So the summation as n goes from 1 to infinity of the absolute value of -1 to the n plus 1 times n squared over n plus 1 to be squared. This is the summation as n goes from 1 to infinity of n squared over n plus 1 squared. And this guy diverges by the nth term test for divergence. So since the limit as n goes to infinity of n squared over n plus 1 to be squared is equal to 1. Here for the nth term test, that is not equal to 0. This implies series diverges. So 5. It'd be neat if we could say it diverges absolutely, but that's not a definition. The series is divergent. Thank you.